the screen for introduction.
No, that is okay,
No, it's
Vanna,
okay.
no
No, no,
problem.
no, please don't.
Yeah,
Let
you
the
Oh,
can
okay,
screen be
continue.
okay,
open.
sir. Okay, sir. So I welcome you all again to the second international conference on mathematical modeling and physical sciences, and we all have gathered here for the keynote address now. So I would take the great opportunity of introducing the chairperson of this session, Professor V.H. Pradhan, sir. Now, apart from performing the administrative duties at the institutional level, Professor V.H. Pradhan sir has got more than 30 years of teaching experience. Under his guidance, 13 students have successfully completed their PhD thesis and 2 students are still pursuing. He has published more than 100 research papers in international journals. He has delivered more than 150 expert talks in various international and national conferences. Professor Pradhan has also organized many short-term training programs and international conferences, and he is now currently acting as the chairman of Medical Advisory Committee in SVNIT Surat. Thank you, sir, for joining with us. We are also esteemed with the presence of our distinguished keynote speaker for today, Professor Dimple Kumar Chalis Hazar sir, and I have already been privileged for introducing such a great personality. It's a great opportunity for all of us to listen to the words of Professor Chalis Hazar sir. So to proceed further, I would like to hand over this session to our chairperson, Professor V.H. Pradhan sir.
Yeah, thank you, Vanna. So we are beginning our first day of the program with the keynote address by Professor Dimple Kumar Chalisar. He's a very good friend of me, and he has always kind enough to accept the invitation. Although you can see the time, it's a very odd hours over there, but he has never refused, and he has always given his consent to deliver. So this shows that his interest towards mathematics and towards academics. So we are always motivated with your such motivations and involvement with our department. So I'm very much thankful to you, sir, for accepting our invitation to deliver as a keynote address. So without taking much time, I will request you, sir, to please start your lecture. Thank you very much, sir.
Thank you, Dr. Pradhan, for such a nice introduction. It is my indeed pleasure to always work with you guys and accept your invitation. Thank you so much. So today I'm going to talk about the controllability of a neutral stochastic impulsive functional integral differential system by a resolvent operator. And talk is just organized like this. First of all, I just would like to give you the introduction, and then after preliminary. In introduction portion, I will just give you that how this title justifies controllability, neutral, stochastic, impulsive, functional, and resolvent operator, such kind of things. Whenever you are working with a stochastic problem at that time, one has to be very careful about the preliminaries. Preliminary makes a big difference. And then after, we will switch over to the controllability result. Then after, I would just like to give you the applications of our theoretical portion. Then after, the conclusion, and finally, what are the future works based on this work? At the end of the talk, if time permits, I just would like to go over the appendix in which I have proved one theorem, and I just would like to highlight that thing to you guys. And finally, the references which I've used to prepare this talk. So let me first start with the introduction. As I told you that what we actually mean by the controllability. So controllability is one of the fundamental concepts in mathematical control theory, and it plays an important role in both deterministic as well as the stochastic system, control systems. Over the past few years, people have been working in this direction, and the controllability generally means that it is possible to steer the system from the initial state to final desired state using the set of admissible control functions, or you can say admissible controls. If a system is not controllable, because sometimes it may be possible, suppose you are working in the infinite dimension space, and suppose the objects, they are the moving objects. So in that case, it may be possible that whatever the point you desire to hit, you may lose that part, you may lose that point. But it is quite interesting, it is quite possible that you are going to hit your object in the neighboring of that point, your desired point. That type of controllability is referred as the approximate controllability. There are some different notions of controllability too, like null controllability, then local controllability, local null controllability, then local approximate controllability, then optimal controllability, etc. And people have been working in that direction. My approach for this particular talk is nothing but the fractional Brownian motion. Why I chose this fractional Brownian motion? Because I know that physics people, they have been using this thing a lot, fractional Brownian motion. Electrical engineering, they're using a lot. And that's the reason, because this is the conference arranged between, I mean to say, by both the departments, physics as well as mathematics. So that's why I just chose this one. So fractional Brownian motion, I just would like to say FBM, that is BHT, T belongs to R, is a Gaussian stochastic process which depends on the parameter that is called the reduced parameter. You can see over here, reduced parameter H lying between 0 and 1. And this stochastic process is self-similarity. It has a self-similarity index, stationary increment, and long-range dependence properties. It is known that the fractional Brownian motion is a generalization of a Brownian motion. And if you take this H equal to exactly suppose half in between, then this fractional Brownian motion is converted in the standard Brownian motion. This fractional Brownian motion has lots of applications. Few of the applications, or most important application, I would say, that is nothing but the finance market, your stock market. Stock market is fluctuating nowadays, you know this thing, and that can be measured, analyzed using the fractional Brownian motion. Fractional Brownian motion can also be useful in our telecommunication network, biological mathematics, and other fields of applied mathematics too. Whenever you are working with any of the control problem, first of all, you need to make sure you need to make sure about the existence, uniqueness, stability, and the asymptotic behavior of the mild solution of the system. This existence, uniqueness, and the asymptotic behavior of the mild solution of class of impulsive neutral stochastic differential equation driven by fractional Brownian motion is the recent development in the field of mathematics, and few researchers, they have been working in that direction. Several upcoming researchers have keen interest to study the control problems in the field of stochastic system. Our approach is stochastic. First time I'm giving the talk in terms of on the base of the stochastic system with fractional Brownian motion. A thorough literature survey reveals that a very little work has been done in terms of fractional Brownian motion. Chen, he just concerned the approximate controllability of a semi-linear stochastic equation with fractional Brownian motion, and several other researchers, they have been just started working in that direction. So my system is like this. You can see over here dxt, and this is not the gamma function. Please keep in mind, this is just the operator. So gamma x txt, script u xt minus t of xt, b of ut, integration o, and gamma, and script a txt sigma dbh. Here, script u is nothing but the infinitesimal generator of a strongly continuous semi-group t of t, where time t greater than or equal to 0. And bounded linear operator b is a bounded linear operator. U is a control function, and that takes a value in L2 0 to t interval to u, admissible control function with u as a Banach space. This is nothing but my fractional Brownian motion. Let me just go over the system components. Hilbert space is X with the domain of script U. OT is a closed linear operator on X with domain of U is contained in domain of O. BH is a fractional Brownian motion with reduced parameter. In particular, I just would like to take H greater than half, means my interval is the open interval half to 1. I will let you know why. I'm taking this half to 1 on a real separable Hilbert space Y. As I told you, U is my control, and it comes from the space L2, 0 to U, admissible control function with U as the separable Hilbert space. B is a bounded operator from U to X. My history, xt. Now, guys, look at over here. Whenever you have this xt, you can see this x suffix t. You can see x suffix t over here. You can see xs here. You can see xt here. That means all these operators, they have some history. History, I mean to say some delay part. There are two types of delay. One is finite delay, one is infinite delay, and I will let you know about this with examples after some time. So whenever you are working with some history at that time, you cannot work with the usual general Banach space or Hilbert space. You have to specifically define some particular space, and that space is known as the phase space. So we are going to talk about this phase space after some time. Whenever I use the word phase space, it is to be understood that we are talking about some history, some delay portion, delay part. Fine. So history xt, that is negative infinity to, because it is negative infinity, and that's the reason I just put this thing in the title, that I'm talking about the infinite delay problem. So negative infinity to 0, history part 2x, such that xt at theta, that is equal to x of t plus theta, belongs to an abstract phase space BH. I'm going to define this axiomatic definition of phase space after some time. My operator gamma and A, they are from 0 to t to phase space, because as I told you, they contain xs delay portion history. That's why it comes from this phase space. And sigma from 0 to t to L to 0 yx, we will discuss about this space too, are the appropriate functions where this L to 0 to t denotes the Q Hilbert schematic operators, Hilbert space, but Q Hilbert schematic operators from y into x. The fixed moment of time tk, 0 is less than t1, t2, t3, up to tm, and that is less than t. xtk minus and tk plus represents the left and right limit of xt at time t equal to tk respectively, and delta xtk, you can see over here, delta xt equal to tk, that is the jump in the state x at time t with my impulse. You can see with my impulse determining the size of the jump. So this is the system component, and now I just would like to switch over to my preliminary. As I told you that we are talking about right now the stochastic system, and that's why we have to be very careful about the preliminaries. Preliminary, that is just a platform for our other work. Fix the time interval 0 to t, and because it is stochastic system, that means everyone knows this thing, that we are working in the probability, complete probability space. So my omega script f and p be a complete probability space, and bhtt belongs to 0 to t be a one-dimensional fractional Brownian motion with reduced parameter lying over here, half to 1. Just now I told you that I'm going to work with half to 1. This BH, my fractional Brownian motion, is a centered Gaussian process with covariance function given by this one. Look at here, covariance function, this one. This BH has a following Wiener integral representation. I mean to say that this fractional Brownian motion can be approximated by the Wiener integral in some particular sense. Why particular sense? Because here you can see this beta is nothing but the set beta tt belongs to 0 to is a Wiener process. So this is my Wiener process, and the kernel kh is given in this particular form. When you define your kernel at that time, you have to make sure about your CH. CH is given in this particular form. Once you have your CH, this G in the bottom, in the denominator, that is your beta function. So first you define your beta function. According to your beta function, your CH has been defined. Plug that value of CH over here. That will give you your KH. That KH you need to plug over here. And that particular Wiener integral is to be approximated by this fractional Brownian motion. That's what I mean. Okay. We will denote the script H, the reproducing kernel Hilbert space of fractional Brownian motion. That is my script H. And the indicator function 1, 0, t belongs to my interval with respect to the scalar product. You can see 1, 0 to 1, 0 t, that is nothing but the covariance function, RHTS, like this. The mapping, my indicator function 1, 0 to BHT can be, that is a fractional Brownian motion, can be extended to an isometry between H and the first Wiener chaos. That's fine. Let X and Y be two real separable Hilbert spaces, and let Lyx, that is the space of bounded linear operators from Y to X. Q belongs to this space. Q is an operator belongs to this space and defined by Q. En is equal to lambda and En. But what is this actually? This is nothing but this finite trace. So that is the trace of Q. That is just the matrix and the finite trace you can see. And that is finite. Summation of lambda n. When lambda n, all lambda n runs from 1, 2, 3, and so on, they are greater than or equal to 0. And on non-negative, you can say, and the real number En, this En is nothing but the real numbers and is a complete orthonormal basis in my separable Hilbert space Y. And we define the infinite dimensional fractional Brownian motion in Y with covariance Q given by this one. So fractional Brownian motion in terms of covariance, that is Q, the definition is like this: BHT is equal to BHQT and summation of, with the help of this trace, I am defining this Q Hilbert, I would say covariance Q of fractional Brownian motion. So lambda En, and Bn H. So it's a sequence of, you can say, sequence of fractional Brownian motion. Is all these fractional Brownian motion, they are independent, real and independent. And this process that is Gaussian, it starts from 0 and has a 0 mean, and covariance given like this one. All these things are proved in the literature, so I don't want to go out the proof of this one, just accept this one. To define the Wiener integral with respect to the Q fractional Brownian motion, we introduce the space L20, from which if you recall our system, our sigma operator comes from this space. So L20, that is defined by L20 Y2X, Q Hilbert-Schimich operator. So whenever our sigma comes at that time, we will consider that one from this Q Hilbert-Schimich operator. So that is nothing but actually the collection of all operators like this psi from Y2X, or you can say sigma, whatever you want to say. We recall that psi belongs to this one, is called the Q Hilbert-Schimich operator if it satisfies this norm of this summation that is finite. And this L20 of space, L2, of course, L20 Y2X, that space is equipped with this norm. From inner product of phi and psi on L20, there is nothing but this one. And this is, again, a separable Hilbert space. I just would like to define one function from 0 to t to L20 yx. The Wiener integral of this function phi. Now I am talking about Q-Schimich Hilbert operator and the Wiener integral of this phi with respect to my fractional Brownian motion. So Wiener integral in terms of fractional Brownian motion, that is defined like this one. Integration phi s dBh, that is equal to summation of this one. Here, what I did, just previously I told you that this BHT, this definition, I have plugged this value of BHT over here, and we are getting this estimation integration of this one, that is equal to summation of integration of this one, and that is equal to this one. Where this Bn is nothing but, Bn is the standard Brownian motion used to define my fractional Brownian motion, means just plugging the values as I told you. Consider this operator KH star. This KH star actually, that is the space from this indicator kernel to L2 Hilbert space, of course, to L2 0 to t, and defined by KH star phi s and given by S to t phi s del KH over del R RTS. After looking at this expression now, those who are working in the field of functional and real analysis, they must be knowing this thing, that you can always switch the derivative. I mean, by integrating by parts, you can always, in partial derivative, you can always switch the derivative. What does it mean? That means let me first tell you that this KH star is an isometry between the Hilbert space H and L2 0 to t, and that was proved by Grimmer. Thanks to Grimmer, it's a big proof. KH star is the isometry between H and L2 0 to t. And this BH star is now approximated. My fractional Brownian motion is approximated by this BH star. But if you look at the construction of this BH star, you will now surprise this thing that, as I told you, that you can switch the derivative. I mean to say that we are not just working with the operators or the functionals, we are working with the distributions. And when the distribution is there, that means naturally we are talking about a Sobolev space. Very nice book. At this point, let me just recall to the authors, I mean to say the researchers, new researchers, those who are working in the field, those who have pursued their PhD. Let me just let you know this thing, that there is a very standard book based on the distribution theory and Sobolev space. Our Indian author, respected Indian author, Kesavan, he used to be the professor at TIFR Bangalore when I was doing my PhD, but then after he shifted to Med Science, Chennai. And I got the opportunity to meet him and discuss some of the things with him when I met him in ICM 2014 conference in Seoul, South Korea. Nice person, but very fantastic book. And those who are working in the field of partial differential equation in any of the universities on the globe, on the world, you will find that book in the rack, in that university, in the library. So that's the prestige of that book. Distribution theory and Sobolev space. First chapter, distribution theory. Second one is just Sobolev space. Third one is application. First three chapters are the main, I would say, fantastic, really, really good chapters of the book. And that's enough to understand the distribution theory. Anyway, let me just continue. So Grimmer, he said that the elements of H, they are not just functions, but as I told you, the distributions. And in order to obtain a space of functions contained in my script H, Hilbert space, separable Hilbert space H of indicator function, we consider the linear space norm of H generated by the measurable function psi like this, and norm of psi that is given like this. This norm of psi that is defined by alpha H, alpha suffix H you can say. But this alpha H that is actually defined by H to H minus 1. Now guys, look at over here. Initially I state that my Roost parameter comes from 0 to 1, open interval 0 to 1. But then after I restricted my Roost parameter from half is excluded, half to 1. Because if I take half over here, I'm going to get alpha is equal to 0. That means I can't define this thing. So just for the sake of convenience and to proper construction of my formulation of my problem, just I have considered my Roost parameter that is strictly greater than half, and that works over here. One lemma. If collection of all psi, all operators from 0 to L to 0yx satisfies this integration of norm that is finite, then phi is well defined. Phi, I mean to say that this one, this winner integral of my operator phi with respect, winner integral of my operator phi with respect to fractional Brownian motion, this one is well defined, except I mean, provided this condition holds. And here you can again find 2h minus half, 2h minus 1. So I can't work with h equal to half because otherwise this one will not work. So for the well-definedness of my equation 5, I have to have my Roost parameter. I have just compressed my condition. Now let's talk about the phase space. The phase space BH is a linear space of function from -∞ to 0. You can see the history into the separable Hilbert space X and out with the sup norm. First, we present the abstract form of the phase space like this. Suppose that a continuous function h from -∞ to 0 to infinity. So h is the, you can say, bridge between your history and your control, your future. So your 0 to t. So h -∞ to 0 to infinity endowed with L equal to integration of this h s ds that is finite. We define this phase, this space, phase space. Phase space, again, it's a Banach space, or here you can say probably separable Hilbert space, but in some particular separable space. At this point of time, I will give you the proof of this one also. That's what I have proved, and I'm going to, if time permits, I just would like to give you the proof at the end of this talk. But again, if time permits. And this phase space, that is a collection of all psi from -∞ to 0 to x for tau greater than 0. Estimation of psi t square is bounded and measurable function on the interval -tau to 0. You must be wondering that here I have considered -tau to 0, and here I said tau greater than 0. That means if you take suppose tau equal to 5, here it comes -5. Tau equal to -10, here it comes -10. That means I'm approaching to infinity like this. And integration of ht sup norm of this estimation that is finite. This construction with this space is really, really important. This is endowed with the norm of psi at BH that is equal to this one. And this one, of course, is a Banach space. You can take this any Cauchy sequence and you can prove that Cauchy sequence is convergent to the same space. That means the non-linear space is complete, and complete non-linear space is a Banach space. Everyone knows this thing, easy to prove. Let me give you now the history of this space. Last year when I gave a talk in the first international conference, at that time, I discussed a little bit about the delay problem. I just would like to continue and extend that delay problem over here. First of all, let me just give you the practical delay problem, finite delay problem. Then after we'll talk about the infinite delay problem. And then after I will continue with the same point. Let me just look at the time because I don't want to run out of time. Oh my gosh. Okay. So suppose somebody, unfortunately, met with an accident before 2 hours. And immediately people gathered. And then after nice people took that guy to the hospital, and doctor just tried to did the initial checkup, and doctor came to know that there are some internal injury in some of the organs of the body. So doctor now it is essential for the doctor to know when this accident took place. Where is not important, but when it is important. He lost that patient, he lost some blood, and knowing on the history, suppose accident took place at 9 a.m. and he was brought to the hospital at 10:30 or 11 a.m. And if doctor comes to know this thing, that the accident took place before a couple of hours and that patient has lost this much of blood and there are some internal injury in the lungs or something like this, and now doctor can decide based on this time span, loss of blood quantity. Based on this one, doctor can decide whether to go for the transplant of the organ or he can do the surgery and use the same organ and try to make the surgery successful. So this is the biological application. This type of delay that is called the finite time delay problem. There are some infinite time delay problem. Infinite time delay problem doesn't mean that the process had started before our birth. No, it's not like this. Infinite time period means the time period is absolutely impossible to measure. That's what I mean by infinite time delay problem. I discussed this problem with, I think, Professor Jayesh Dodia when I was at SVNIT. Suppose, let me give you again the biological problem, the same example. Suppose a patient is really, somebody is really very particular about the health, and he goes for the doctor every year just for the body checkup. In February 5th, 2021, when he went to the doctor, at that time, doctor, after all the urine test and blood test and all other examination, doctor said that he was absolutely fine. That is, he's a very healthy guy. But this year, on 5th of February 2022, again, he goes to the doctor, just a routine checkup, yearly routine checkup. But this time, after blood check and urine take, after some test, now doctor figured it out that that guy is suffering from some cancer or diabetes. And patient got disturbed. How it is possible? I'm really very diet person, keep myself healthy, and how it happens. That's okay. But now he wants to know that when that process exactly started in the body, because last year there was no any kind of symptoms, but now he is detected diabetic, he is detected cancer patient. When that, nobody can predict. Suppose he asks the doctor that, please doctor, let me know that when this process started in my body, when that disease entered to my body. Doctor cannot say that it was on, suppose, 15th of September, 10 o'clock, 5 minutes, 3 seconds. No, doctor, nobody can tell this thing. Nobody. It's impossible. Whenever you are dealing with this type of problem at that time, this problem would be considered as the infinite time delay problem. So infinite time delay, again, that is not like this, that process has started long back without knowing any time. No, it's not like this. It is a time which cannot be measured in practice. But that's what I mean by the infinite time delay problem. Okay. Unfortunately, that whenever you are working with a time delay problem at that time, people had been using the definition given by Hall and Kato, Japanese mathematicians, because time delay problem that has started before 15 years back. And people worked on the same problem for almost 10, 12 years. Around 2014, 2016, 2015, 2016, when I was reading the literature, unfortunately, I just went through one of the books written by Hino Murakami and Nito, again, Japanese authors. And they mentioned this thing very clearly. They say that if you're working with the infinite time delay at that time, you cannot use the phase space given by Hall and Kato. You need to define the separate phase space with some additional conditions. And I was curious to know this thing. And then after I worked on that particular things for I would say one and a half years. And I figured out this thing. So this is the phase space, and that paper that was published in Journal of Optimization Theory and Application, Jota Springer, and one of the papers that was in JMA elsewhere, Journal of Mathematical Analysis and Applications. So I defined this space, and then after, now people are just well aware of this thing. But that time delay problem, this space, whatever I defined, that was just for dynamical system. That was not for any fraction, or I would say the stochastic process. Stochastic time delay, I extended the same idea in 2019, and now 2019, 2020, COVID time. And now the same idea can be extended for the stochastic process too. And that's what I have added in the appendix. Okay, so this is just a history about all time delay problem. And now let me just let you know, let me continue with my process. So consider the space script BDI. D stands for delay, I stands for impulse, because both conditions are there in our system. So such that dBi is a collection of all operators x from negative infinity to t. Now it is a combination negative infinity 0 and 0 to t. Negative infinity t 2x. That means it is a very useful space now where x is a ik is a restriction of x to the interval ik. Interval ik, there is open interval tk to tk plus 1. Closed interval tk plus 1. That means if you take k equal to 1, I'm going to get t1 to T2. T1 is excluded, T2 is included. But if you go to the next stage, if you take k equal to 2, T2 is excluded and T3 is included. So everything, that's why it is called the impulse term. So this ik belongs to, or sorry, x is restricted to ik and that comes from that is nothing but that comes from the space of all continuous functions from ik to x, and left and right limit both exist, and x0 minus phi belongs to my phase space, and supreme of this estimation that is finite. This BDI endowed with a norm like this. I'm talking about a stochastic process. You can find my estimation everywhere. Suppose x belongs to dBi, then for all t belongs to 0 to t and xt from the phase space, because x suffix t, that is the delay part, comes from the phase space, such that L of estimation of this one that is less than or equal to this one, where L is nothing but integration of Hs that is finite. Partial integral differential equation in Banach space. Just let me give you a little bit about this thing. Further, we collect some basic results related to the resolvent operator. Like script U and O are closed linear operators. Script U, infinitesimal generator of a semigroup, and O, the closed linear operator on X, and Y represent the Banach space on domain of script U, equipped with the graph norm, this one. Notation C, that is a space of all continuous function from this interval to Y. We know this thing. We consider the following quasi problem. I just consider this quasi problem because I want to define the resolvent operator with respect to this quasi problem, and then after I can extend the same idea by including some nonlinear operators. A resolvent operator, Pazzi is the best book for semigroup theory and its applications. Resolvent operator is being discussed in the book of Pazzi, P-A-Z-Y. A resolvent operator for equation 6 is boundary linear operator valued functions RT in Lx, satisfying these three conditions. R at 0 equal to identity operator. My resolvent operator is norm that is bounded by the exponential function m and lambda is positive. For each x in x, RTX is strongly continuous, and for each x in y, RTX that belongs to the common domain of the space of all differentiable continuous functions from interval to x and the continuous function from interval to y. And this R dash t that is equal to script u RTX integration 0 to t is OT minus S RS, and you can commute this one, this RT and script mu, and you can write RT minus S. If that is possible, then in that case, that operator is known as the resolvent operator. Already I gave you these two conditions, but now I specifically I need these two conditions. So let me just put in my assumptions H1 and H2. My H1 assumption says that the generator operator script U generates strongly continuous semigroup T of T on X. For all T greater than or equal to 0, OT is a continuous linear operator from Y into X. And moreover, there exists an integrable function C such that this operator Y to theta Ty belongs to the Sobolev space, because I told you that they are nothing but the distributions. And this d by dt of OT operating on T at Y on X, that is bounded by this one. If these two assumptions are satisfied, these two assumptions hold, then there exists a unique resolvent operator of my quasi problem 6. If that is possible, in that case, I can get the there exists a unique resolvent operator for the quasi problem 6. So existence of the resolvent operator, because resolvent operator that is useful to get the mild solution of the system. And that's the thing I'm just trying to explain to you about the resolvent operator. One more estimation we require, that is for the resolvent, there is nothing but the property of the resolvent operator, the resolvent RT plus epsilon minus R epsilon RT, and its norm is bounded always. Now I just would like to add, in that quasi problem, I would like to add this my continuous function. And a continuous function x from my 0 to infinity to x is said to be strict solution if x comes from this common domain and x satisfies equation 8. Now guys, look at over here. If you're in the finite dimension, in that case, if you have a system and you can go for the solution, then you can go back to the system again by derivative integration process like this. But once you are the infinite dimension space, and suppose you have the differential system like this, or integral differential, what it may be, first order, second order, doesn't matter, and you write the mild solution, it is absolutely difficult, impossible to go back and get the system back. Once you have this solution of the system, then after you cannot come back on the same part to come back to the system. It's not possible. And that's the reason we are using semigroup, cosine operator, sine operator, resolvent operator like this. And that's the reason we consider that one as the mild solution. Anyway, please refer the book of Pazzi, chapter number 4, mainly chapter 4. A continuous function, okay. if my two assumptions H1 and H2 hold good, and if X is strict solution of equation 8, then by variation of constant formula, look at over here, this is X dash, and now I'm writing the solution of my this system, that is XT is equal to RTX0 integration RT minus SQX ds. Look at over here. So I use this resolvent operator to get the mild solution of my system like this, XT or like this. And that's the thing. This thing I'm going to use to get the mild solution of my problem, the main system I showed you on very first slide. Okay. Let me again show you my mild solution of the system using the resolvent operator. So now I'm in a position to define the mild solution of the system, and that mild solution of the system that is given like this: xt equal to RT and phi 0, blah, 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 and resolvent operator, bounded linear operator, my U control, and sigma, L2 space, from L2 space, my fractional Brownian motion, and impulse condition. So my mild solution of the system, that is this one. A function x from 0 to infinity to x is called a mild solution if it satisfies the variation of constant formula. For the control part, I'm going to use over here the Krasnoselski fixed point theorem. Let V be a bounded, closed, and convex subset of a Banach space X, and pi 1 and pi 2. Pi 1 is just the operator over here. Pi 1 and pi 2 be two operators of V into X, satisfying pi 1 plus pi 2 belongs to V. Pi 1 is a contraction. Whenever I want to put pi 1 is a contraction, at that time, what I'm going to do, just go back and go look at this mild solution. I would like to send everything on my other side, my left side, except my nonlinear function. Or I would like to bifurcate this one in terms of one operator. I would like to bifurcate one part, suppose theta 1, with the linear operators, and second part, theta 2, with a non-linear operator. Why? What is the reason? Because if you have a linear part, you can easily prove the contraction. Once you have, and if you assign the map, that map is a contraction that can be proved using some assumptions. And whenever you have non-linear part, at that time you have to be careful, because pi 2, as I told you, that I'm going to take all my non-linear part with pi 2. So pi 2 is a completely continuous operator. Guys, just look at over here, functional analysis, real analysis, and control theories, guys. Whenever you are working with the finite dimension, at that time, compact implies closed and bounded, and closed and bounded implies compact. That is very obvious. But if you are in the infinite dimension space, at that time, compact implies closed and bounded, but the converse is not true. Closed and bounded don't imply compactness, right? And that's why, thanks to Arzela Ascoli, or Ascoli Arzela, you say, thanks to these two guys, they said that if your operator satisfies, if your operator is really very strong continuous, like equicontinuous and relatively compact, so equicontinuity plus relatively compactness will provide you the compactness. So that's the theme I'm going to use over here. The pi 2 is completely, and every completely continuous operator, there is a compact operator. So that's the theme I'm going to use over here. And there exists an operator Z in V, such that the Z, whatever operator I had, that can be written as a combination of pi 1 plus pi 2. And once I do this thing, that means I'm getting the fixed point, means I'm getting the controllability in probability space of a stochastic system. Now I'm going to start my preliminaries. Almost done, it's done. And now the controllability result. System 1, 2, 3, you know that control definition varies from system to system. Here, based on my stochastic system, my control definition I have written down like this. System 1, 2, 3 is said to be controllable on the interval negative infinity to t if for every initial stochastic process phi defined on my delay part, history part, there exists a stochastic control U is a control from L2, as I told you in the very first slide. We steer the initial stage of the system to the final desired state in time t, initial state phi to final desired state x1 in time t, such that mild solution of my system xt, mild solution of the system satisfy xt equal to this 0 to t, capital T, that is my final desired state, and that is equal to capital that final time. So at time t, my system achieves the final desired state on time t. So xt, where x1 and t are the pre-assigned terminal state, that is xt, and my pre-assigned time, final time, that is by t. To prove this controllability result, I just require a few of the assumptions over here, that my resolvent operator is bounded, and my operator gamma from the interval to history to Hilbert space satisfies the following condition: estimation of this one kind of Lipschitz continuity and supremo of gamma that I would like to denote by some gamma k gamma bar. Also, my operator gamma, script A satisfies the carry theory condition. I mean to say that function is measurable with respect to first variable and continuous with respect to second variable. And for any k greater than 0, there exists an L1 function pk such that my gamma function is bounded by this L1 function. But this L1, if you pass the limit as k tends to infinity 1 over k, this L that is always finite. That is always finite. I would like to denote by R. There exists some constants mk and mk bar such that my impulse condition satisfies a kind of Lipschitz continuity and it's bounded to. My sigma condition, sigma operator from 0 to infinity to L to 0, integral of norm that is bounded to. Whenever you are working with the control problem at that time, just make sure that you are going to write your mild solution and you are extracting your ut from your control from the mild solution. That means you want all the things on other side except your ut. So for that, you require the invertibility of the operator. Whenever you write the invertibility of the operator, at that time, make sure that there should not be any null operator, zero operator, because if zero operator is there, you cannot send to the other side. It doesn't make sense. And that's why we have to extract that part. Here in our term, mathematical term, we can say kernel of W. So we need to extract that one, kernel of W from my space. So that is actually this linear operator W from U to X defined by WU, that is the inverse operator. That this is W inverse, but actually it is W tilde inverse because we are working in the quotient space, not in the full space L to 0 to U. We are restricting, we are subtracting this one. So we are kernel of W, that is this one. So we have to remove this part from my space. So that is a restriction. And once you have that restriction, then after you can proceed further. Without that, you cannot even define your control. You can see over here, W tilde or W inverse appears at the initial stage. For this particular space or system, I have defined my control like this: W tilde inverse equal to X1, final desired state, and my final time, blah, 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 and so on. With this condition, my system is controllable. If I assign some operator phi defined on BDI like this, so my, psi xt, that is defined like this. On the history part, it is phi t. Otherwise, on t belongs to 0 to t, I have this estimation. It's just the mild solution, nothing else. I just assign an operator. It is now obvious to get the mild solution of the system 1 to 3, and that's is similar to the fixed point of operator sign. So to get the mild solution, and if I am able to prove that this operator psi has a fixed point, I'm done. I'm getting my complete controllability, or you can say exact controllability. Let y is an operator from negative infinity to x be a function such that yt is defined like this. And for each z belongs to my space of B, delay and impulse Hilbert space, set xt equal to zt plus yt. Xt equal to zt plus yt means whenever xt appears, whenever this xs here, whenever xt appears, at that time I need to write zs or zt, yt like this. Look at here. So my zt now will appear like this, zt plus yt, then z plus y, zs plus ys everywhere. My control u will be now defined in terms of, because now it is not x, is z plus y, so z plus y, and so on. At this stage, I just would like to define one subspace beta di0, that is collection of all operators z from BDI such that z0 equal to 0. With this space that is endowed with a norm like this, and that is again a Banach space. Now I would like to define the same mild solution, but in this subspace, particular space, I would like to design, I don't want to say psi, but I just would like to assign another operator. Let me say theta. So theta is from BDI 0 to BDI 0, same terminology, same thing. And let me define BK, that is a collection of all z from BDI 0 such that my z is bounded, z square is less than or equal to k, is bounded. So my BK is contained in BDI 0, is a bounded closed convex operator. And first of all, let me just check this boundedness. So zt plus yt is bounded. I would like to say r square. Estimation of uz plus y is bounded. I would like to say g. And I just would like to go for the decomposition of my operator theta in terms of theta 1 and theta 2. I already explained to you that theta 1 contains just the linear operator, theta 2 contains the nonlinear part. So theta 1, I can prove easily the contraction. Theta 1, theta 2, this is the Krasnov-Celsky fixed point theorem condition requirement, and that's what we are going to work over here. Theta 1 is a contraction. First of all, I'm just going to prove that theta 1x and theta 2x belongs to BK. Let me use the contradiction method over here. Suppose this statement is not true. Not true, I mean to say there exists at least one operator from BK which is not a part of theta 1 plus theta 2. And that means I have an estimation that is greater than K. Reverse way, I can write K less than this one, and I have this estimation. I would like to consider this one here to here to here. That is by some capital K bar or something like that. And I can divide by K. So dividing both the sides by K, I'm getting this estimation. I skipped some of the steps over here because of the limitation of time. And limit K tends to infinity. This infimum of the limit PR star divided by K, that is equal to this estimation. I just divided and multiplied by this R star. And thus we have this condition, 6L square that is greater than or equal to 1. But our assumption says that, you can see over here, our assumption says that less than 1. But I am getting greater than 1. That means whatever I have assumed over here, that this statement was wrong. Actually, it was my fault. I was wrong. So I should have not assumed like this, means this statement is correct. Theta 1 is a contraction, very obvious to prove. Theta 1, Z1, theta 1, Z1 square, Z1 and Z2, not square, sorry. Theta 1, Z1 and theta 2, Z1, and just plug the values and you can get this estimation. Not a big deal. Theta 2 is a completely continuous operator. Complete continuity means first I need to prove the equicontinuity. So theta 2 is first I prove the continuity over here. Equicontinuity is a more stronger concept. Then after I went for the theta 2 maps BK into equicontinuous family of functions, and I proved the equicontinuity over here just using by assumptions H1 to H8, and just plug the values and I'm getting these estimations. And this is the equicontinuity. Right hand side is independent of all operators G from G in PK and tends to 0 as tau 1 minus tau 2 tends to 0. And since the compactness of R implies that continuity in the uniform operator topology, and therefore beta 2 maps BK into equicontinuous family of functions. And finally, I proved that theta 2, okay, I think still I have 10 minutes, okay. 15 minutes, okay. So theta 2 BKT is pre-compact set in X. Right, so let me consider theta 2 epsilon ZT for 0 is less than epsilon is less than T and Z belongs to BK. This is the estimation. You can see over here, just I use the definition of theta 2 with this epsilon, with this condition, 0 is less than epsilon is less than T, and I'm getting this estimation. And I have the operator, close operators, theta 2 tilde like this defined in this form. If I combine this one in this form, theta 2 epsilon and theta 2 tilde epsilon, and just plug these two values over here, and we can define this V epsilon tilde T that is equal to theta 2 tilde theta tilde, you can say 2 epsilon Z T, where Z belongs to BK, is a pre-compact in X by using the total boundedness, and then Z belongs to BK. And the estimation of this one finally gives me this one. So estimation, this tends to 0 as I take epsilon tends to 0 plus over here. So you can see over here that there are pre-compact sets arbitrary close to my set VT theta 2. So there are pre-compact set. The pre-compact set, I assume this theta 2 epsilon tilde is the pre-compact set arbitrary close to my set V2, set of V2, Z belongs to BK. And hence set VT is also pre-compact, and by Arzelà-Ascoli theorem, theta 2 is compact. And now everything is satisfied by Krasnov-Celsky fixed point theorem. There exists a fixed point Z for theta on BK, and we define Zxt equal to this one. And it is easy to say that X dot is a mild solution of the system satisfying the terminal condition Xt equal to X1. So that's how I got my controllability result theoretically. And now let me give the application in terms of the heat equation. Big system is there. Consider the neutral impulsive stochastic functional integral differential equations with infinite delay. You can see over here. And this is my delay part. x, this is nothing but my whatever my script u was there in my system, that is here it is nothing but del square by del square psi, kind of heat equation. BH over here, that is my fractional Brownian motion, but here that is in the form of the cylindrical fractional Brownian motion. And phi is from negative infinity to 0 cross 0 to pi to r is a given continuous function. Actually, yeah, given continuous function, stochastic process such that norm is finite. My separable Hilbert space, I just would like to consider x, y, and u in terms of L to 0 to pi with norm, this one. And my script u, infinitesimal generator of a semigroup, resolvent operator or semigroup, you can say that domain of script u is contained in my separable Hilbert space x to x, given by u equal to, as I told you, del square, that is this one, del square, with domain of u, that is collection of all operators y from y in x, such that y is absolutely continuous, y double s in x, and satisfies this boundary condition. Thus, this script u, that is means ax, means you can say my semigroup is defined in this particular form, n square x en and en, where en is nothing but square root of 2 over pi sine nx. This is the orthogonal basis of eigenfunctions in script u. My phase space, I have considered hs equal to e to the power 4s, s is less than 0, and if you take the integration, you're getting 1 by 4, and 1 by 4 is finite. We know this thing. So first condition of my phase space is satisfied over here for this particular problem application. My phase space, phase space BH is a Banach space. We know this thing with the norm given like this. To modify my problem is this 7 problem, I would like to say 17. To modify this problem in the abstract form, we assume the following, that T psi comes from, because T comes from this interval, this phi is the history, so phase space, and phi theta psi, that is equal to phi theta psi. And we have put this one, gamma and A, these are in our system here, and sigma, they are in the system, but here particularly I can define my gamma t xt minus k sigma in this form, and script A, that is defined in this form. So above systems, whatever system 17 as an application I just represented to you, that can be written in the abstract form of my original system 1, 2, 3 and my theory. And that's why further we can say now just the control part. So B is a bounded linear operator defined by this one. For this particular problem, this bounded linear operator, there is that is nothing but the C psi ut. C psi ut. This is my bounded linear, because this is my control U, and this is my bounded linear operator B is nothing but C psi over here. So that is my C psi, and that satisfies the invertibility operator like this. So W u, that is defined in this form, kernel of w, that is given like this, one collection of all x in L2 such that wx equal to 0 be a null space of w, and kernel of w, orthogonal complement of w, you can say, in L2 0 to u. And this w tilde is from orthogonal complement of w to range of w. Both are in Banach space, of course. So inverse mapping theorem says that w tilde inverse is bounded, because both are in Banach space, as I told you. And so w tilde inverse is bounded and takes the value in L20t to quotient space like this. That means condition 8, invertibility of the operator w condition, is also satisfied over here for my system 17. So thus it is possible to verify the assumptions given in theorem 3.1. And therefore, I can claim that my system 17 is controllable on negative infinity to t. Conclusion. So here what we did, this research work is concerned by the controllability result of impulsive neutral stochastic functional integral differential equations driven by the fractional Brownian motion with fine infinite delay in a real separable Hilbert space. Controllability results are obtained using the stochastic analysis, Krasnow-Celsky fixed point theorem, and the theory of resolvent operator in the sense of Grimmer and fractional Brownian motion. We have used the new definition of phase space for the infinite delay time interval. A practical example of heat equation is provided to illustrate the viability of the abstract result of this work. Future work. Last 2 minutes. Okay, I have 5 minutes. Okay, sounds good. Future work. Based on this work, this paper is accepted for the publication in Research in Communication and Optimization RICO elsewhere. Recently, I just got the message of the acceptance before a few days. This paper, based on this one, you can create multiple research articles, and I can say that we can produce more than 5 PhD theses. Yes, you must be wondering, but I'm sure. Look at over here. We can study the controllability of the system considered here driven by fractional Brownian motion, not for time dependent, but now state dependent finite delay as well as the infinite delay. 1 or 2 papers. We can consider the controllability of fractional neutral differential system driven by fractional Brownian motion for infinite time delay or infinite state delay. The fractional system. I have just considered the ordinary system, differential system, stochastic system. You can consider fractional stochastic system, and you can use the Kaput or Riemann-Liouville derivative and Kaput derivative. You can work on that direction. You can refer a few of my manuscripts. We can, all of them are on ResearchGate, so you don't have to worry about it. Or you can send the email to me. We can consider the controllability of the fractional neutral differential system driven by Rosenblatt process. There's the advanced version of fractional Brownian motion. So you can just extend this problem to Rosenblatt process for infinite time delay as well as state delay, another 3 papers. We can extend the controllability of optimal controllability of the fractional neutral differential system driven by Rosenblatt process for infinite time and state delay. Look at over here. One can also study the controllability of the fractional neutral differential equation driven by fractional Brownian motion or Rosenblatt process, whatever you think, for the distributed time or state delay. Distributed time delay is a little bit easier than the state delay. When big concept, trajectory controllability, I defined trajectory controllability before 5-6 years back. And that was for the dynamical system. My next target is to define the trajectory for my stochastic system too. So you can produce more than 50, maybe 100 research articles based on trajectory controllability. This is the new direction. I just opened this problem for you. You can work and you can publish the papers. I don't mind. That's fine. So trajectory controllability of above problems will be the new investigation or development in the field of stochastic analysis. One new thesis you can produce that is based on numerical estimation. Stochastic problem with numerical estimation, that is, I don't find enough literature based on this one. One can pick up this one, take this one as challenge and prove the results. Last one, again, one more thesis. You can use the PDEs like parabolic, elliptic, or hyperbolic extension of the stochastic problems to stochastic fractional order time or state delay problems. They are the open problems too. So as I told you, lots of applications are there. Appendix. I told you I have 5-7 minutes. Okay, so let me just go through this appendix very quickly. These are the actually definition given by Hole and Kato, which I explained to you in the form when we discuss about the delay problem. This Hole and Kato, and unfortunately, people had been using the same definition for the infinite delay, but that was not true, and that's what I proved. And then after we discussed this one, I proved this result. You can see over here. I think if the organizers and the committee members, they are kind enough to send this file to me, I would like to put this one on YouTube so that you guys can go over these things very slowly and you can read this one thoroughly. And if you have some doubts, you can contact me, because let me just first finish this part. This is CB, the space, whatever I have BH, I just change the name, but script B suffix H, that is my phase space with this norm and this estimation, and proof is given over here. You can see the proof. And finally, I proved, look at the last line, I have proved the same thing for my stochastic problem, and that is done. So finally, yeah, since last 55 minutes, almost I would say 50 minutes, I have been talking you. I just let you in my domain of mathematics, and I just don't want you to go outside of my domain. If you guys are interested to work, that's fine. Just send me your email, send the email to me, and I will try my best to reply you if you have some doubts. There are some references I have used to prepare this manuscript. You can see over here, Grimmer, the most important reference. And finally, I have 3 YouTube channels. One channel is on my name, Dimple 40,000. You can see over here, lots of research works, whatever the talk I have delivered. Not all, but some of them, they are there. So you can find my talks, some of my research work over there. And I have included some of the courses which I'm teaching over here at undergraduate, graduate level. So you can find, or you can come to know how United States, how we are teaching in the United States, how it is different from the teaching in India. All these things you will come to know over here in this channel. Suppose you are getting tired of all this higher mathematics, fine. And if you are a spiritual guy, then I have another challenge, that's divine light. You will find lots of spiritual videos on divine light. I have uploaded so far, I think 45 or 47 videos on the spiritualities, on Indian ancient Vedas and Sanatan Dharma, if somebody is interested. And if you are not a spiritual guy, don't worry. And if you love to listen to the music, just go to the Sur Sargam channel and you can find some music. But I just would like to let you know in my domain. I'm just kidding you. Thank you, guys. Thank you for your support. Thank you for your kind cooperation, for patience hearing.
Yeah, thank you, Professor Chalisazar. It was really a wonderful lecture. I hope participants will be definitely benefited with your lecture. And if the participants have listened to the lecture very carefully, then you can see that how he has presented and how at the end he has shown you that there are so many scope where one can go in that direction. So thank you so much, Professor Chalisazar. It must be almost 12:30 a.m. at your end.
I would say exactly it is 12:45.
Yeah, 12:45 a.m. over there. So I can just tell the participant that you can see that even at the midnight, how effectively he was presenting. So this is only possible only because he has got so much interest with the field of mathematics. So we are very much fortunate to have the keynote address on the very first day. So thank you so much. And as per the decorum, we are not allowing the participants to ask any question to the keynote speaker. That is why they may not be able to ask you any question. But in case if they have got any difficulty or any communications they want, they will definitely correspond with you. And of course, so whatever you requested us, we will provide you the link. We can put it on YouTube also. And we will also try to visit your YouTube channels. Of course, I have visited few of them, and it's really enjoying, and it's really
Thank you.
encouraging. Yes, yes, yes.